All right? Okay. So, good morning. So, it's a real pleasure to be here. I can't believe I'm lecturing and I'm looking over the canal. It's so beautiful. So, this is the probably fourth or fifth time it happens to me over the last 10 years that I'm in a room like that with 20, 30, 40 people who are studying climate change, and they are scientists, economists, engineers. And I'm either the only psychologist or one or two, three psychologists. And so every time I enjoy it, every time I come to one of these meetings, I learn a lot, and so this is no exception. But I can't help but ask myself why I am here. Why did they bother to invite me? So one theory which I have, and I can't reject it, I don't have data to reject it, is just for comic relief and entertainment. And I don't mind. See, that's what we call in psychology priming for mood. Okay, so, and I don't mind, but I think that by the end of these two lectures that I'm going to give today and on Friday, you'll get a sense that there is some valuable contribution from the behavioral, psychological analysis and thinking about uncertainty to be gained for people who are working in this topic of climate change, which is of so general and wide interest and affects everyone in various ways. So roughly speaking, I try to divide my two lectures. So today it's mostly about uncertainty in a most general way, the way psychologists think about uncertainty. And although I'll allude here and there to issues related to climate change, I will present a few examples from my own work in the talk on Friday. But I'll probably, I probably won't be able to finish everything I have here today. So on Friday, I'll talk a little bit more about risk perception and a few examples about work on climate change. So this is kind of a quick overview of what I hope to achieve. I want to, first of all, convince you that it's relevant for the climate change community to learn about the psychological component. I want to, because some of the things I'm going to be saying overlap to some degree. We're saying that Aaron said, we're saying that Bill Nordhaus talked about. I want to kind of clarify a little bit terminology and not notation, terminology only in terms of the way we talk about things and compare to other, and to emphasize some of the things that I think are important to us in the JDM community compared to the economist. And then I'm going to talk about several topics. I'm going to talk about the issue of judgment of uncertainty, elicitation of uncertainty, so to speak. I'm going to talk about this idea of combining probabilities from multiple sources in order to come up with a single value that in some sense represents the common wisdom of the whole crowd. So this is all on the judgment side, and then I'm going to talk a little bit on the interaction between a communicator and a decision maker at the other end, and give you some examples of the way we think about individual decision making under uncertainty and under what some people call ambiguity, I will call vagueness, or in general imprecise information. If there's enough time, although I'm going to say a few words about social dilemmas under uncertainty, which is really not the topic, but it has a clear bearing on issues related to climate change. And then, as I said, I'm going to probably leave the risk perception stuff for Friday, for the first part of my talk on Friday. So the reason I think this work is of relevance to people who are not psychologists are threefold. And you can think of them as pertaining to the application of the models, and to basically setting up the models, and in some sense, personal level. So regardless of how good and accurate and perfect a particular model is, and how accurate and useful the model's implications for policy are, the models are not going to be adopted, they're not going to be implemented by the decision maker, political decision makers, unless they are accepted. And for these models and their consequences and their results to be accepted, endorsed, and implemented, there must be a way for the scientists at the one end and the policymakers and all the other stakeholders to communicate effectively and basically to have a common understanding of what one of them is communicating to the others. And I think climate change is one of these cases where there's been a lot of miscommunication. Much of it has had to do with the way people talk about it, and the fact there are many stakeholders who do not want to see policy, to prevent or reduce climate change implemented. And one of the things that these people have done very effectively is essentially to use uncertainty as a strategic tool, as a way to dismiss results and to put them down and to downgrade their importance. And if you ever watch television shows and this about court cases, and I always come to the court and say, so can you say that this is with a medical certainty, as if such thing exists? And then the witness kind of said, well, not certainty and so on. Okay, so if you can say it with certainty, then we're going to dismiss and ignore everything you say. And I think that kind of has been in many, many places, especially in the United States and some political circles, the attitude to climate change. As long as there's uncertainty, we need to do more work, we need to do more research, and nothing has to be done, nothing has to be changed. And I think that this is a real problem, and therefore I think the ways of thinking about communicating uncertainties is critically important. The other component, it really is that the realization of with which you are more familiar even than I am, that many of the models involve uncertainty. Many of them involve a variety of distributions that need to be estimated, elicited from experts and so on in order to let the models run. And therefore, so you need to say, well, what's going to be the shape of this distribution? What are its parameters? And you need to get as good an elicitation of estimation from experts to get to where the models run. And I think that our work on probability elicitation is highly relevant. Thirdly, like everyone else, regardless of whether you are at one end, namely decision and policymaker, or at the other end, a scientist who works on model, whenever I think you learn, you think about how we as human beings, generally speaking, deal with uncertainty, there's something that you learn about yourself and that can guide and help your own thinking and your own work in this respect. So these are the three arguments in favor of why you should pay attention. Okay. I want to say a few things. In some sense, they are a reaction to a couple of comments that Bill Nordhaus made yesterday. So our discipline, which we refer to as judgment and decision making, or JDM, is essentially a small group or small subset of people in psychology. We are somewhere along the border or the interface between social psychology on the one hand and cognitive psychology at the other hand. And we deal with the way in which people perceive the environment, make judgments about the environment, articulate and verbalize these judgments, and then how they use this perception, or either internally generated or received from external sources, to make decisions in the presence of uncertainty. And so we think that we study decision making. Clearly, other people think that they study decision making at different other levels. So the models that you've heard described yesterday were essentially normative models, and in some sense, you can think of them as being models of the decision problem. So if this is the decision and this is the function that I wish to optimize, and these are the constraints, and I'm adopting a particular set of conventions about what is normatively correct, then, from Neumann, Morgenstern, or Savage tradition, these are the axioms, and if I accept this axiom, then it means that I must act by choosing action that maximizes expected utility. And there's a sense, if you think about them, of this being general, universal. The axioms are compelling and they're all accepted, and therefore what we need to do, given this axiom represent our common thinking about decision problems, this is how the problem needs to be analyzed, this is how we need to act. The descriptive or behavioral component or facet takes a different look at it. We are not so much interested, but it's not that we are not interested, we are not primarily interested in the analysis of the problem, but we are interested in the analysis of the decision maker. In other words, how does a particular decision maker or a group of decision makers, when faced with this particular problem, are dealing with it, and how are the actions that they intuitively or after deliberation and thinking and analysis, not necessarily using the formal tools, act upon them and what choices they make. So in principle, there shouldn't be a conflict between the two. And in principle, whatever is normative is what will also be accepted and adopted and implemented by everyone. But in practice, quite often, there are differences. We can point the start of our profession to a particular paper in 1954. Ward Edwards, who some of you may know of or may have known him when he was still alive, published a paper in Psychological Bulletin. It's called Behavioral Decision Making. And he is the one who for the first time articulated and communicated psychologists much of the work from decision theory, from the mathematical decision theory, and illustrated through some experiments and some examples ways in which things which are considered to be normative and unquestioned under this theory are violated by people who face the same kind of decisions. Yes?
I mean, I have trouble understanding why they assume that the decision problem is what decision makers face. So,
what do you mean?
I mean, when I use, I have first a normative approach. I try to understand what is actually happening in the framework.
Mm-hmm.
And then I know that I have to go through implementation problems, and so I try to design an institution such that the decision makers, optimally acting in some behavioral way, will deliver what is something for me or from my ethical perspective. In that case, the decision problem is not what the decision makers have. They don't need to have this normative criteria. They just have to behaviorally decide what to do in their own criteria, and then what is the result is what I want to.
Okay, so I'm not sure I can give you a compelling and complete answer at this point, but I hope that maybe probe me again half an hour maybe from now, when I think that some of the things will become clearer in what I mean. So, but I think that what happens is that there's an assumption that there's an underlying, maybe implicit assumption in what we are doing, that people who make decisions want to make them in a way that is optimal. People want to, even in cases where people want to optimize, and in some sense they would benefit from having a formal analysis or going through the whole process, which oftentimes they don't have the time, and most often they don't have the capabilities of doing. Okay, and I think that's. What we are trying to do is to contrast ways in which these two things are different and to see what we can learn from these differences. So, this is a distinction that we all make, and I think it's overdone in the following sense. First of all, even people who do purely normative, right? So say, the example that you had, I don't care that you show me that people think that 2 + 2 = 5, okay? It will still not be normative, okay, to act accordingly and to prove theorems under the assumptions that 2 and 2 plus 2 are 5. So the same thing you can say about many other behavior. I don't, you say, you tell me thou shalt not kill, yet people kill every day, and therefore that's not a reason to adopt a particular code of normative actions. But I think what you want to learn from that, that most people, most of the time, think that 2 + 2 is 4, and most people, most of the time, don't kill anyone. But there are circumstances, there are cases, there are particular individuals who are more likely to make this kind of decision. And through the analysis of the situations where these discrepancies, these violations between the two emerge, that you can learn why is it that sometimes people think act as if 2 + 2 is 5. And I think that from the psychologist's perspective, it is through these cases where there's a conflict between what most people would probably accept as, yes, that's a principle, and behavior that they exhibit which violates it, that you learn something about the psychological mechanism that drive decision.
So is it correct to say that you assume that the institution in which the decision makers operate is exogenously given?
I don't even think about it in these terms, so I have a hard time. I have a hard time answering.
If you're thinking of judges taking a decision, they have a normative idea of how the decision should be made, but then you look at their behavior.
That's a good example. Yeah.
But
yeah.
You are not questioning about how many judges should be in the room. That's something that is given.
In principle, it could be given, but you can also think of circumstances under, when in fact, when I'll talk about aggregation of probabilities, you'll see you can think of situations where the nature of the data kind of dictates some solutions that could be used to change the institutions. Okay? So for example, you may not start this work this way, but I think I can have a relatively good and robust answer as to, if you want to average probabilities of many experts, how many experts should you take? Okay? So this distinction between the normative and the behavioral. And the other thing I should say about most of the work that we are doing, it's not that we don't like theory and value. Yes, we do, and we like and we value and respect. But when you look as an outsider to our work is very, very much phenomena and data driven. And because Edward started us on this path, so here's the normative model and this is how people behave, isn't it interesting that, in these cases, they follow the rules, in these cases, they violate in systematic ways. What can we learn from that? And so we've been kind of driven and also excited by these discrepancies and these sometimes call them paradoxes. I think that these have become the ways, the leverage that we are using in our work to basically learn something about the way people think. And so quite often, we get very hung up on particular small results simply because they are so interesting and so unexpected. And if there's one single empirical result that kind of guides everything that we've done, is that quite often, more often than you would expect, things that should not make a difference from a theoretical or normative perspective make a difference, and sometimes a big difference, in the way that people think about the problem, perceive the problem, analyze it, and act upon it. So I'm going to say a few words about something that Aaron mentioned earlier, that the three ways of thinking about what probability is. And like I think practically everyone who deals with uncertainty and probability, we are a little bit confused in the way we think about it. So there are the three interpretations, the classical Laplacian interpretation that all elementary events in the sample space are equally likely, which is very much driven by analysis of games of chance, of course. Then the von Mises-Reichenbach analysis of relative frequency, so that probability is simply something that you observe in the long run, and in the limit, although there's no guarantee that there is a limit, so there are all kind of mathematical inconsistencies there. But the idea is that, just like you do with insurance, life tables, you have millions and millions of live births, and you can calculate how many of the people, men and women, live to that age. And there is the subjective personal probability, which is typically associated with Ramsey, Bruno De Finetti, and Savage. And in some sense, the distinction is in how do you say it? The relative frequency says that the probability of an event is, because it's somehow objective. Everyone who observed this million times tosses of a coin will agree on the count. And the other one is my probability is. So. It's easy to dismiss, and I think in many cases that the various definitions are indistinguishable in their, estimates, in their prescription of what to do. But in some cases there are, and in our field there has been a lot of debate, a lot of controversies about whether certain results that we are finding are real and are general, or they are all due to the fact that not everyone thinks about probabilities in the same way. So in other words, that if you accept a subjective view of probability, which I definitely do, and then all the probabilities are subjective. I don't know how many of you remember De Finetti in the first chapter says there are no probabilities. All probabilities are subjective, right? So in the sense that dismissing altogether any idea of objectivity or common agreement about what probabilities are. So, but yet, even if you accept this, probably De Finetti would not argue with the fact that if you toss a dice millions of times, the probability that it lands on 1, 2, 3, 4, 5 is 1/6. So I don't think that subjective probability come into play only when there are no long-term frequency. I think that having long-term frequency is a necessary but not a sufficient condition to invoke an objective probability or relative frequency consideration. So I'm just mentioning just kind of a background because a couple of times later on I'm going to point out to the distinction how it matters in the way you think about probabilities. What are the sources of probabilities? So generally speaking, and this also has a long history in philosophy, there's a distinction between two types of uncertainty, what people like to call the aleatory and the epistemic sources. And essentially aleatory has to do, is everyone, I mean, maybe I shouldn't say this thing, is everyone familiar with this? Okay, great. All right, so I already feel better. So the idea of aleatory uncertainty, it's really uncertainty that has to do with the outside world. It really has to do with phenomena that are driven in your context by the natural forces, and they are driving the stochastic processes that govern nature. And so essentially what you can do, you can observe the environment and get estimates and try to understand what are the distribution, right, and the probability of various events. From your perspective as a decision maker, right, I mean, or as a judge, the way to get to these aleatory uncertainties, so for example, that will be a way of saying what is the probability of random, for any given randomly selected given day in Venice, that it will rain more than 2 hours a day, okay? So this is something which clearly one can quantify by long-term, long-time observations and quantification of, of this phenomena, precipitation in Venice. And by using long-term observation, you can tally and, and obtain a view of this phenomena. So that's why I'm saying this is the distributional outside view. You are an outside observer, and you are observing the environment and create, either by formal or kind of informal tools, this idea of what is the distribution in nature that govern that. And that we are contrasting this with epistemic uncertainty, which is of internal sources. So the questionnaire that Erin administered 2 days ago asks you to make judgments about the population of Cuba, how many canals there are in Venice, how many people voted from Eisenhower in 1956, and so on. There's no uncertainty about these things. These things are fact. These things took place years ago, and there is a one and unique answer, so there's not a random variable. But when you think about them internally, there is epistemic uncertainty, because your knowledge about this information, which in some way in principle is known and fixed, is uncertain. And it has to do with your having incomplete, imperfect information, or not having complete access to your memory, just a second, from which you are going to recover them. Yes?
So Google in combination with smartphones has all by the brain data the same type of uncertainty.
What do you mean?
Well, I can look up.
I don't have a Google. I don't have it. Okay. Yeah, I mean, I agree, but the point, I agree, but let me make the following point. The point is that psychologically, the experience of not understanding something about the environment, the frequency of precipitation, or the distribution of temperature in a particular location, and this idea of not knowing or not having information and not having access to the information are different. The way in which people are dealing or are trying to resolve the uncertainty of epistemic sources is through reasons, think, well, what are the arguments that will lead me to think one way or the other? And through experience. I've went through this exercise many, many times before. Is it a good idea to try to walk at home, at 1 o'clock at night, or am I better off calling a taxi and things of that type? So experience and arguments are of that type. The other way in which Google has not solved the problem, at least not yet to my knowledge, is that sometimes probabilities are not about events which have happened in the past, but are forecast about the future. And I'll give you an example in a few moments, because from this kind of context. And you can use Google to precisely to recruit arguments why that would happen or why that would not happen, but not to solve the problem. Again, this is a distinction which is really very nice to have. Most cases, I think, involve both sources of uncertainty. So I think everything about climate change is of this type. It's kind of a mixture of epistemic and aleatory uncertainty, because there's a sense that there are stochastic external processes that you'd like to characterize by drawing their probability distributions. But in fact, we realize that information about them is imperfect and incomplete. One way to think which one is it is to say, if I had perfect access to an unlimited access and unlimited time to all the information, would I be able to characterize and identify this probability completely? That if the answer to this is yes, then it's purely aleatory, or is it a sense that there is something which you can call irreducible uncertainty, which is internal, and no matter how long you'll try and how long you'll think and search on Google or elsewhere, you will not be able to resolve this problem completely. Yes?
Sorry.
Yes?
So in some situations we think of endogenous uncertainty, meaning the probability of events are actually my action changes the probability of event. So when you characterize this as epistemic, in a sense, because or is it just another taxonomy?
It's probably a different taxonomy, and I can't tell whether it is totally orthogonal to that. So because if it has to do with your own actions, this is somehow not part of this. So I don't know, I have to think about it. I don't know. Yes?
When you say that you have unlimited time and all access to all resources, would it also be that knowledge that could be known but isn't known yet? So, for example, time sensitivity.
Right. Yeah.
In principle, it probably could be known perfectly.
In principle, right.
I don't think that.
Yeah. So let me put this. You're right. In principle, we think about this as being aleatory, in the sense that if you had perfect information, perfect measurement, and unlimited observation, you could characterize the exact. No, that would be aleatory. But that will be aleatory. But I think what you'd have to do, you have to say, am I sure that do I have currently models and measurement procedure that would allow me to measure this perfectly? So I think that most cases are a combination of both. So as long as you're not sure that the model that you have and the measurement tools that you have to measure this are perfect, then it's also kind of there's some kind of epistemic uncertainty. Yes.
I'd like to ask under which category this example would be. For instance, I live in a place that's prone to sea level rise, and I'm seeing the seawall being overturned.
Yes.
So I think it changes from an epistemic point of view. It changes my idea of my appreciation
Yes.
of uncertainty.
I agree 100%. Well, I agree 100%, and in fact, I mean, the last point I was going to make is, again, these are two extreme points which are easy to make, to characterize, to frame the discussion, but I think most cases are somewhere in between. And what some people consider pure aleatory, others will think of them as being epistemic, and vice versa. And I can see how in people's mind, availability of new information and revision of probability will say, oh, at this point it has switched from being one to the other. Yes?
During our research, we noticed some those that who are having experience managing or
Right.
like sea level rise, for example,
Mm-hmm.
people who have actually learned about it and failing perceptions.
Yes.
So I wanted to ask, with respect, would that still be based on their experience, as opposed to, if for instance we're trying to like promote adaptation strategies,
Right.
and we're faced with either raising climate change awareness, or as opposed to someone's direct experience.
Yes, so I think that the way in which you think about the uncertainty and the way you evaluate information that you think helps resolve or characterize the uncertainty, first of all, will change from one case to the other. And I think you're absolutely right, that some type of evidence and some pieces of information and different ways of acquiring are more powerful and more compelling than others. Yeah. Yes, I really want to move on, but yeah, go ahead.
Yeah.
No, that's fine.
I feel way more confused than I do before. I don't see any distinction between these at all. I mean, it's more than arbitrary, right? There's actually no, I mean, can you even give an example of something that's epistemic? That if you had perfect information in full time, you couldn't put a probability on it? If it's not a preference, I thought maybe epistemic was preference.
Well,
This seems completely vague and arbitrary and not well defined. I mean, and if one person says it's aleatory and another person says it's epistemic.
well, I guess I don't want. I think I've already overdone it, and there's no walking it back. But I think it's really more than anything else. It's a way to think about how people perceive uncertainty and why do you think there is uncertainty. And I think in people's mind is there's a distinction. There's a distinction between the two types. And let me give you a stupid example that will clarify it. It's an example which is funny, but I think exemplifies this idea. So there's this very nice book by two Dutch psychology, Willem Wagenaar and Gideon Kramer. They've done in the Netherlands, correct me if I'm wrong, gambling is legal and is governed by the state. And Willem and Gideon did, with approval and funding from the state, lot of work on gamblers, people who gamble. Some of them recreationally, some of them professionally. These are, by the way, the people the reason you don't see people tossing coins on street corners, the risk lovers, is because they're all in the casino. Yes. No one's, but anyway, so one of the most interesting results of their study is that people who gamble make a distinction between chance and luck. They understand that the roulette and the wheels and the cards are governed by the rules of probability, and some of them don't know them very, very well. There's no question about what chance is and how it governs. What they think the secret to a good gambler is to recognize your own luck, to recognize when you are doing well, when you feel it, when you're hot, and therefore when to go all in and when to pull out. So this is a distinction. This is kind of a typical example of this type of distinction, is that psychologically you make differentiation between the rules that govern the way the croupier spins the roulette wheel and the way I am making bets. Okay. All right, so I don't want to spend too much time on that. I want to talk a little bit about the typology that Tom Walston and I kind of proposed a few years ago, and I think it's not very deep, but it's very interesting and helps think about what are the reasons or what are the sources of imprecision in communication of probability. And we distinguish between three things. One is the nature of the event itself. Much more often than we care to admit, the things that we want to assign probabilities to, the events, are not precisely defined. They are in fact ambiguously defined. Okay, so there's a nature if the event is not precisely defined. So I'm saying, what's the probability the market will go up in the near future? Okay, so every one of us can, if you want to ask, be precise. Each of us can say, well, near future is a month, 2 months, 4 months. market will go up, we must meet at least 6%, you know, and so on. So the fact that not everyone will understand the question in the same way is in itself a source of miscommunication in probability. And in my opinion, it is one of the most underestimated and underappreciated sources, because the way we communicate with each other is that you say, you know, if we are sufficiently precise, above a certain threshold, that everyone who hears us understands things exactly the way we mean it, and not recognizing that different things may mean slightly different things to other people. The other one, the second component, is this idea of what kind of uncertainty and how well can you resolve the uncertainty? What are in other words, so to think about it, if the uncertainty is precise, then you should be able to draw a complete PDF over it, okay? And otherwise, you cannot. And the third one is, what is the language that we use to communicate uncertainty? So so far we've used almost interchangeably the words uncertainty and probability, because most of us are taught from the first class that we take that probability is the language of uncertainty. But quite often, if you maybe be more sensitive when you hear things in this future, you'll see that people don't always use probability in the precise sense. This probability of this event is 0.27, but they say something, well, it's around 40%, which means I cannot be very, very precise about it. It will say, and quite often people use probability words. It's likely, very likely, extremely unlikely, and so on. So these are different levels of precision of the events, of the uncertainty of the events, and the communication language. And I'll have later on a couple of examples that show how it matters and how this needs to be combined optimally with each other. In other words, how the language should be chosen as a function of the nature of the event. So I want to talk a little bit about probability judgment, or what you could say elicitation. So what are the things that we want to get probabilities for? So we can, of course, as always, distinguish between discrete events and continuous events. So by discrete events, the type that's most often studied is simply a binary event. Will it happen or not? And what's the probability it will happen? And other cases where there are more than two categories. So for example, which team will win the next World Cup in football? Is it going to be Brazil, Spain, Italy, or other? Okay, so in this case, C equal 4. You have 4 categories. And so these are discrete events. In each one of these cases, the way of eliciting probabilities can be one of two. There's a tradition in our field of doing it in 2 stages. So in other words, of saying, do you think what's the probability it will rain tomorrow? So first tell me whether you think it will rain or not. So make a binary classification, and then based on their classification, what is the probability? So if you said it will happen, if you're going to give me a probability estimate which is less than 50%, I'll be surprised, right? And therefore I refer to this as half range, because having committed yourself to a particular outcome, then I expect that this will bound the probability. I expect a probability between 0.5 and 1. Whereas if you say full range, just simply what's the probability of rain. So that's a minor distinction. It matters in the way you model and you quantify it. And then we have judgments of continuous distributions, and I'll give you an example in a second. The other thing that I need to distinguish is that in many of these cases, there's a difference or distinction in the way you make elicitation, whether you're asking for simply direct judgment, what is the probability of that event I'm interested in, or you're making indirect judgments, which are ways of getting to this probability without asking, not in brute force by asking people, but putting them in a situation where they need to take action to make choices, and you can infer the probabilities from their choices. So this is a project that has taken most of my time over the last couple of years, called, you can go to the website, www.forecasting-ACE. This is a forecasting project that was funded, has nothing to do with climate change, although there were 1 or 2 questions about climate change, by the intelligence community. That's basically a way to see how well they can use people everyone. It was open access on the web to make judgments and predictions about events, politics, economics, you name it. I don't know how well you can see. This is an example. So this is an example of a question about what will be the average mortgage rate in the for a 30 years loan in the United States in a particular date. Okay, and everyone could log on to that site, see the question, and decide they want to answer. And they would answer. In this case, what they would do, they would first say, will it be above 4.5 or below? So click 1 or 2, and then afterwards, they could use the sliders, or they could enter a number to see what's the probability of that event. So what you see here is a typical example of direct judgment, right? Because people ask about probability. And in this case, what we've done, since we wanted to be very open and to allow all the participants to find their favorite way of doing it, rather than saying enter a number, if someone prefers to use as a slider and not commit to a number, that's fine. So I would always favor not asking for numbers, but I would always favor a slider, because it avoids a variety of biases and tendencies that have about numbers. And it really, if you just think about the slider, it makes you think more about the probability rather than the number. Here's an example of how you can think about eliciting probability distribution for a continuous function. I'm going to distinguish between two methods. FP, which stands for fixed probability, and FV, which stands for fixed value. So what you have in this case, you have the same cumulative distribution, the cumulative distribution of x as a function of the value of x, and these two are the same. But all I want, what the arrows, which are in different directions, different colors on the two panels, indicate that the way you're making the judgment is different. In one case, on the left-hand side, you say, the x, the target value is 50. What I need you is the expert or the judge to tell me what you think is the probability of finding a value which is above or below 50. Okay? So you fix on x, that's what fixed value, and you ask me to estimate probability. And then I can go through this process by asking, well, now how about 70, how about 30, and so on. And then you can obtain a few points on this distribution. On the right-hand panel, the conditioning is reversed. So in other words, in this particular case, I'm telling you, I want you to tell me, that's the examples that, in your example, what we're asking about, making judgments about the population of Cuba, or the number of bridges in Venice. What is the number of bridges in Venice?
Less than in Hamburg.
Less than in Hamburg? That's nothing. I think I was told around 400. Does it make sense? Okay, anyway, but the point is that in this particular point, you are conditioning on the probability, and you ask people to make judgments about what is the value that corresponds to that probability. So you can do it directly, the way you did it in the experiment. You ask people to make this judgment. One can do it indirectly, which is my favorite way of doing, and this is from a paper that Ali Abbas and I have. And so essentially this is what I call an indirect judgment. An indirect judgment is one where you're not asked to tell what is the probability of the event, but you're going to infer probability from choices. So you're told, okay, you can win $20, but you can win $20 if this was run with students in Ron Howard's decision analysis class at Stanford. And so that was about a week before this targeted. So they were asked to make a prediction about weather in their location a week later. So if you say if the probability is going to win if the temperature is going to be 25 degrees or higher, you're going to win $20, or you can win $20 based on a spin of this wheel. In other words, if it lands on orange, you get 50%. So if you had the choice to bet for $20 on the left, on the right, do you prefer to bet on the wheel? Do you prefer to bet on the event? Or are you indifferent? If you say I'm indifferent and click right here, then I'm not, because then you've essentially told me through your choice that these two have equal probability. If you're telling me, no, I'd rather bet on the wheel, I infer from this that you think that probability of the wheel spinning and landing on orange is going to be, is higher than the probability that the temperature will be above 25, just a second. And then what I'm doing, based on your judgment, and based on which methodology I'm using, I'm going to adjust one of the two. So if you told me, if I want to keep the probability fixed, they say, oh, so you prefer the wheel, then what I'm going to do, I'm going to say, well, how about the temperature being 24 and being 23? And so I can go through multiple iterations until I get to a point where you say, no, I don't care what I bet on the wheel or I bet on the event, then they are equally likely. So that's a way where you never had to say, you as a judge or an expert, were never asked to say, what is the probability of? But by expressing preference to bet to win a particular prize, I can infer your probability. Yes?
So how much are you allowed to investigate before you make your choice? Because I have no universe so I would definitely.
Well, I mean, this is a method. Many people can use this method in a variety of ways. We can use this method. So when we ran this experiment, the experiment was programmed in such a way that people didn't have access to the web, or you're right. You could go to Weather Underground and see and get the probability distribution of temperature or precipitation, whatever it was, in Palo Alto in the month of December. I don't want to answer this question because I don't care. So it varies in the following way. If I am hired by a big company and they want me to come in and to help advise their people to plan and to make predictions about the market, I'm going to spend with them to answer this kind of question the whole day. Decision analysts do this. I mean, they go to the whole day and because you want to help these managers to extract the information they have inside and to provide them tools to do it. Okay, and they say, well, let me look at this report, let me look at that. And we've done this. I can tell you maybe later about one or two cases. And you can do it. If you do an experiment, you simply write a program where people are allowed to make 4 or 5 judgments, and if after 5 iterations they haven't converged, you say just arbitrarily stop and so on. So this is just a tool which can be used in different ways in different places and with different orientation. So in an experiment, for example, you may ask, let me just show you something and then I'll go back. So here's some results from this experiment where the green points and the blue points are the results of people estimating the same distributions, once with fixed value and once with fixed probabilities. And then we fitted beta distributions to each one of them, and what you see in parameters these are generalized beta distributions. So the typical beta goes from 0 to 1, but you can also extend its range. And so you can see that in all of them, the last 2 numbers are just the range, so they are the same. But for example, if you, let me use this. So here's the 2 that are very, very different. So this is people making judgment about temperature, and they were using Fahrenheit degrees because they could choose their own. So that's the 2 beta distributions. So one has a parameter of 128 and 1.5. The other one has 135, 165. And the range was 45 to 80. And the range was actually self-selected by the judge, because before we actually did the judgment, what do you think is the lowest conceivable temperature for next week? What do you think is the highest? So they gave us a range. Then what you do, to be on the safe side, you extend the range by another 10 or 20% to allow for maybe they have underestimated, and then we ask this question. So first of all, you see they are very, very similar. But what, so for all practical purposes, probably wouldn't matter. But it's quite clear also, it was quite clear, because we administered questionnaires and surveys at the end, that people find it much, much easier, much more natural, and they finish much faster situations in which they are given a quantity and asked to assign the probability to a quantity, rather than giving a probability and trying to find the corresponding quantity, which is the natural way of thinking. Yes?
So I might have missed this, but how do you choose your anchor? So how do you choose the quantity that you use?
Well, so this is the plumbing portion of it. Okay, so the one way to do it, typically, so you start with a range, And then one very convenient algorithm for doing it is through successive bisections. So you start with a range, and then you start with probability of 50%, and then once you establish it, then say, well, let's say halfway between 50 and 100. But you don't have to do it this way. You can do it in a variety of ways. So okay, so the other point in which this can vary, and this actually was a lot of conversation with the reviewers about this. Oh, I can do that. Do you do this in a way which you really want to understand? As an experimental psychologist, J.D. Emmer would do this experiment. So after we establish what's the 50th percentile of your distribution, then we randomly decide, and now I'm going to go to 90th percentile and 20th percentile, randomize everything. A decision analyst wants to help a decision maker. You don't trick them by randomizing in order to control for carryover effects. And you do it in a way that enforces monotonicity in their judgment. So let's start with the 40%, move to the 50, 60, and you help their thinking. And so again, this is just a tool that's flexible enough to handle both types of approaches. So these are not the only methods. So Dan Golson, who's a colleague of mine who works at they used to be Yahoo Research, and now they've been purchased. They've been bought by Microsoft, so now they are Microsoft. They changed loyalties overnight. But anyway, so they have this method which is very intuitive in the sense that basically you have a small computer program that says, here are 10 bins, and you have 100 balls, and you click and you begin to distribute balls in the 10 bins. So essentially you have people actually draw a probability distribution, and they are using it in a variety of contexts, especially helping people in financial decision making and so on. So that's a kind of another one. Something that we are working on right now is basically to use a method, an indirect method of comparing events without judging probabilities, but then infer the probabilities from their choices. So the idea is the following. You take the whole range of the distribution and you chop it into various values. So x between 0 and 10, between 10 and 20, between 20 and 50, between 50 and so on. And then, so you have a mutually exclusive and exhaustive partition of the range of values. And then you show people pairs at the time, and you ask them, would you think it's more likely that x will be between 0 and 10, or that x will be between 70 and 80? And not only tell me which one is more likely, but how much more likely. Give me a ratio judgment, okay, to illustrate this. So here's an example. This is from the ongoing dissertation of my student Han-Hui Por, and Han-Hui is working on using this approach for joint probabilities. So in this is a 2x2 table where S and C stand for smoking and cancer. So people are asked, think of a random sample of 1,000 people from the US normal population of adults, and there are people who smoke and have cancer, who smoke and don't have cancer, who don't smoke have cancer, and so on. And for each, they see each one of these pairs, and they ask which one is more likely to find in a random sample of individuals and how much more likely. So you generate this matrix, which of course is it has 1 on the diagonal, right? Because that's an event in itself. And it's a reciprocal matrix in the sense that each two mirror image terms multiply to 1. So for example, let's do a simple one. People think it's 7 times more likely for someone to be a smoker and have cancer than to be a non-smoker and have cancer. And of course, they think it's 1/7 likely. So once you complete this matrix and see there are only 4 probabilities to estimate it, but you have 6 judgments, right? 4 things taken care of. So there's a redundancy in the system. And then what you can do some kind of estimation method to estimate each one of the values. So in this particular case, she's using he takes the geometric mean of each row, which in this case is the log least square estimate. And then since this solution is unique up to multiplication by a positive constant, what you do, you take this, overall, the sum of all these, the geometric mean is 7.3. You divide everything by the sum, you make everything add up to 1, and you come up with the following probability. In this particular person's mind, the probability of someone being a smoker and having cancer is about 8%. probability of being a smoker and not having cancer is about 25%, and so on. And you can use this to calculate the marginal, the conditionals, everything, and we've never asked anyone about the probability. The word probability was never mentioned. No one was ever required to make a numerical judgment. So, I mean, I think that's my personal bias, that this is a good way to go about it without forcing. The question? Yes?
So what if you were doing like climate sensitivity, you have an infinite range, so one of your bins would be
That's right.
1,000 NFL.
That's right. Yeah.
And so then you have the problem of cutting it up into different bins, so you might want to do it a couple times.
That's right. And you know, and you're probably, I don't know, you're probably the only one in this. So Bob Clement and forget her name. Who? No. No, his former student, I forget her name, Ulu.
Yeah, Jana. C-A-N-A-N.
Okay, so they have a paper about, they talk about internal additivity and so on. And what they are using, they are not using this machinery of ratio scaling, but they are talking a lot about what are the best way to divide, I say to divide the continuum such that you can get.
Their theory to get
right,
your theory.
That's right, yeah. And in fact, one way to test the robustness of this procedure is to use the same method with various division of the domain. Yeah.
Would you think this is more useful for experts, medical experts as well as the lay audience? I mean, would you prefer this tool even if you were to?
Well, I mean, I think, what do you mean by expert? So if you think a couple of very old paper by Ellen Winkler and Ellen Murphy and Bob Winkler, and there are two types of experts. There are domain-specific experts. There are people who are expert in climate change. There are people who are toxicologists and whatever. So they're big experts in their field. They know the literature. They have lots of experience. That doesn't mean that they have any kind of expertise in probability, or in judgments, or with dealing with number. And there are people who are very good about, their expertise is essentially how to convert and communicate or articulate internal judgments into number. So I don't think that being expert in a particular domain of science or economics also makes you an expert in being able to. So I think I would like indirect methods, even working with experts. Yeah. So we've done work with EPA many years ago, for things where the EPA is the Environmental Protection Agency in the United States, and they are charged with the need to establish thresholds for certain pollutants in the air. And the Congress has a law that says, that it has to be such that the most sensitive subpopulation will not be at serious risk. So now the EPA takes this vague language and they have to come up and say to people who emit lead, this means so many particles per cube millimeter. And they don't have any information to do that because sometimes this needs to be done at levels which are typically not found, and there's no experimental work, not even with animals. So one way to do it is to go to the experts and try to encode their probabilities and to establish here's the dose response and this is the threshold. And even working with experts in that field, they found it much easier to work with comparison between the event that will happen or the wheel. We didn't try this method. So about that. Okay.
Quick question about the indirect method, sorry. But the one with the spinner especially, are you not worried about like ambiguity aversion? Because that's what she was saying. She's like, I don't know about Palo Alto, so I'm taking the spinner. Right, without knowing anything about it, she wasn't.
Well, I mean, yeah, but you're right. But that's
I'm just curious.
no. Well, I mean, yeah. But I think since you don't know about Palo Alto, I wouldn't ask you about Palo Alto. I would come and ask you about the weather in Madison, Wisconsin.
Right.
So that's because that's where your expertise lies. So.
But nevertheless, if it's a hard question, I'm just saying some people are ambiguity averse. There's some concern that they're going to pick the spinner even when they think their probabilities, they're actually indifferent in probabilities,
all right.
So they're going to bet on the spinner. So I've heard that, just curious.
Ali and I have a paper in Journal of Mathematical Psychology showing that in fact it really doesn't matter that much.
That's what I was curious. No,
Yeah.
I like the spinner method, but I've heard that.
Yeah, I know.
You've actually done anything explicit. Okay.
All right, so I'm going to skip this because this is really okay. How do you know the judgments that the judgments you have obtained are good? How do you judge their quality? So I'm going to make the point that there are, so this is again, that's something that Tom and I did many years ago. We have a review in management science about this. And what are the measures of a good probability judgment? So first of all, it has to be reliable, which in our world means stable. You know, if you do the same thing repeatedly, you have to have high consistency between them. So there's the direct impact of random error is relatively small. The key requirement is the second requirement, which is the coherence, in the sense that you want probability judgments to be internally consistent so that there are many judgments of the same, of related events will be coherent and consistent and not contradict each other. So let me give you two examples. The first one is what I call static consistency. So for example, if you ask people to estimate the probability, say the example I gave you about smoking, I'm asking you what's the probability of someone who smokes dies within 10 years, and you give me a number, and then 20 minutes later I'm asking what's the probability of someone that smoked that much does not die from cancer. So these are probability judgment, independently generated probability judgment of complementary event. You want them to add to 1. So that will be kind of the simplest example of internal consistency. You would like, for example, probability judgments to adhere to other basic, like the Frechet bound. The Frechet bounds, if you don't remember, it's basically the statement that the joint probability of A and B is bounded from above and below. So any probability of A and B cannot be larger than the minimum of probability of A or the probability of B, and cannot be smaller. That's a slightly more complicated expression, PA plus PB minus 1. Okay? So in other words, there are certain constraints, and if you get people to make judgments which are inconsistent with that, that means that you cannot trust their judgment. Here's the Linda example. Does anyone know about Linda? All right, so here's a classic example of how people violate this and why they violate it. So there's this story about this woman, imaginary woman, Linda. And I can tell you about Linda that she is, when in college she graduated, she majored in philosophy. She was very active in social causes, and she was involved in several volunteering, she was volunteered in a variety of organizations helping her community. And so you begin to get a sense of who Linda is. You can almost see her and smell her. Now I'm asking you a bunch of questions about Linda, and you tell me how likely that each one of these following things will be correct, will describe her. Linda is active in the feminine movement. 1. Linda is working as a bank teller. And many other questions, and also another question that Linda is a feminist and a bank teller. Now, see, P of A and B cannot be larger than P of A or P of B. Yet, when you do this with many people in an experiment, many people think that the answer is if it's more likely that she is a feminist and a bank teller, then they think that she is a teller. Why? Because she is so prototypical of this particular instance, right? And so that causes you to assign judgments in a way which violate probability theory, the basic requirement of probability theory. So I'm going to give you one more example later, but this is the idea. So if you get a set of probability judgments for a variety of events which don't cohere, that aren't consistent with each other, then you cannot really call it a probability judgment. The other one, and that's going to go to the thing that we talked about yesterday, is a dynamic Bayesian updating. So you want, if someone is if you want to treat someone's probability judgment as correct or meaningful, you want them to be in line with, for example, Bayesian updating. Think of the following experiment. I have 2 urns. They are opaque. You cannot see their content, but I can show you that I put in one of them 70% balls red and 30% black. So 70 red. And in the other one, I put the opposite, 70 black and 30 red. Doesn't have to be That's what I have. I have 2 balls. 7. One is mostly red and one is mostly black. Now, you counted. There's no question about the composition of the urns. Now, what I'm doing, I am tossing a coin, and I am selecting one of them. You don't know which one of them. And then I take them away, and all I'm going to do is to draw with replacement balls from this urn and tell you what I have. Red, red, black, black, red, red. Every time a new outcome is observed, is announced, what you need to do, you need to tell me what's the probability that I've sampled from urn A or urn B. So essentially, if you're a Bayesian, right, what you need to do every single time, you adjust your prior, you start with a prior of 0.5, and then when you heard red, you said, oh, let's favor this one, so now my probability, my posterior, that is the second urn, is 0.7, and then I take another sample, you adjust according to Bayes' theorem repeatedly independently. Now, the question is, are people Bayesian? When people run to this experiment, will their probability judgments conform to Bayes? And the answer is qualitatively yes, quantitatively no, in the sense that the vast majority of participants or subjects, we used to call them subjects, now we are politically correct, we are not allowed to call them subjects, we call them participants. We don't subjugate them to our will. So anyway, that's the APA, okay. So what people are realizing is, in this particular case, is that whenever you see red, it favors one urn, at the expense of the other. So most people, most cases, update in the right direction. They recognize that the signal favors one urn or the other. But if you compare the probabilities that they assign to the probability to obtain from Bayes' repeated application of Bayes' norm, the Bayes' rule, they are conservative. They are too regressive. They are not adjusting their probabilities fast enough. So I think that's what you were asking yesterday. And in fact, the way you can do it, the easiest way to imagine it, if you write Bayes' rule in a log odds form, which is to me the most natural one, so log posterior equal log prior plus log likelihood. Is everyone with me on that? Right? And so what you that essentially fits to a log posterior, subjectively, log posterior equal log prior plus some multiplier C less than 1 times log likelihood. So in other words, you are underestimating the impact of evidence by putting too much information on the prior. Okay? So again, yeah.
Those 2 last examples, when this one out, don't they just pointed that difference between the normative model that you initially pointed out, how people should behave and how people actually behave, let's say because of computational constraints. Because I do not act based on Bayesian updating, because even if I have to do the pen and paper, I'm still very oriented.
Well, that's because you're an economist. I'm just no, okay.
The point is, that's not how actually things behave.
Okay.
Heuristics, as in the first example, or in the second example, I'm sure you're not an anchor, but why do you assess how closely these heuristics link to actual numbers?
Right. Well, so the point is well taken, but I think that actually you've answered your question by bringing together these 2 examples, because they're not alike. Because in the Bayes context, in the updating context, it's really one where people have the right intuition and they have the right thinking, the right way of thinking, but they are computationally inefficient. And in fact, one of the lessons you could learn from that is how to optimally combine judges with a machine or a system, is that you want them to make the basic judgments, what matters, what's the direction, and to let possibly the calculation to the machine. But the Linda question is not one of the same type, because the Linda question, there was a violation, there was an ordinal violation, which cannot be, it is the case that probability of a joint event cannot be larger than the probability of its constituents. Therefore, you cannot attribute this to calculation. It's really something which is that goes beyond computations. And I agree, some of them are pure calculations and some of them are not. Okay, so yes? If you had what kind of effect?
If it was just a calculation effect, then the errors would be on either side of it.
Yeah, well, I mean, that's a good point also. But I mean, but let's be generous that it's going to be the error distribution doesn't have to be symmetric. And in this is particularly one case where that's clearly not going to be symmetric, because you're operating with probability which is on a bounded scale, and it's bounded from above, and it's bounded from below and from above, and errors are always asymmetric and more skewed toward the center. So if it's really 0.9 and you're making an error about it, you're much more likely to underestimate it than to overestimate it. So error doesn't have to be symmetric. So I'm left a note, a blank line before I'm talking about the other two, is because I wanted to point out that these things, reliability, coherence, and convergence, namely that different methods will come to similar results, apply to all probabilities. They apply to subjective, objective, and so it doesn't really matter which one it is. The other, which are at the bottom, which is external validity and calibration, are methods that really implicitly link probabilities to real life realization, and therefore they are much more consistent with an objective view or relative frequency view of probabilities than the subjective one, because as Definetti said, there are no probability, and therefore why would you bother comparing them? But what these are basically a way of thinking of, to what degree my probability judgments correlate with true rate of occurrence, and calibration, which I'll spend a moment to talk about. So this is a typical calibration curve, and this is a calibration curve that was reproduced probably without permission millions of times. This is as good a calibration as you can get. So what this is performance of many thousands of forecasts by weather forecasters in the Chicago area, where they had to make predictions about what's the probability it will rain in the next 24 hours, okay? So, and then each one of these points basically tells you what they take all the probability forecasts, which are on the abscissa, and they are binning them. So, for example, okay. So these are all the cases where people said 25. There are 567 cases where people said the probability of rain is 25, but if you look, it rained about 20% of these days. Or here are all the cases where people said 90%, or in 100 days people said 90%, and that corresponds roughly to 90%. So what we call calibration in this context is to say that the forecaster is well calibrated if the probability of events that actually occur matches the probability they predicted. And a perfectly calibrated expert would have points along the diagonal. This is as close, as perfect that you'll ever see in real life with real judges to calibration. Because these are really, these are the most calibrated, the best calibrated forecast. Why? Because they do it on a daily basis, they get immediate feedback, and also they are being paid or reinforced with a variety of scoring rules, which I'll explain in a second. Okay, so that's the standard. That's what you would like people to be. Yes, you had a question?
You can imagine the downside cost of not forecasting rain when it does rain is greater than if you forecast rain. Somebody's to carry the umbrella.
I understand, but this is, do you remember that expected utility has an independence axioms? So you need to distinguish between quantifying your beliefs and probability judgments and thinking of the outcome. So if I'm a probability forecaster, I cannot take into account the various utility.
That's not their published forecast.
I'm sorry?
That's not their published forecast.
What do you mean?
In other words, you could actually compute these data just by watching the news and see what it rains on.
Right, but these are their forecasts. The basic data are their forecasts. But all I'm saying is that if you're in a situation where you need to make a probability forecast, you cannot allow yourself to basically make these probability judgments be tainted or contaminated by utility consideration. Because if you send them out to thousands of people, that means that they need to be equally useful for 1,000 utility functions. So so that's, I'm going to make this point later when I talk about desirability for a second. Okay, so this is the way to basically see what we mean by calibration, and this is the way we break it down. Okay, so I knew this will not, well, this was a mistake to turn to PDF. Anyway, essentially what we do, we calculate a Breyer score, which this should be right here, a Breyer score, which is the summation across all items of the probability assigned to an event and the value, the true value of that event, which can be the event happens 0, 1 if it happens, 0 if it doesn't, and you take the sum of square deviation, the average sum of square deviation between occurrence and judgment, which ideally would be 0, because if everything goes along the line, then, the sum of square deviation between the x and the y coordinate is 0. The nice thing about this measure is that you can break it down, you can decompose it into 3 components. One, which really has nothing to do with the judgment, is simply the variance of the outcome, because sometimes you're predicting rain in places where it rains 60% of the time, sometimes predicting rains in places where it rains 90% of the time. So the first component is simply the variance of the binomial distribution of that particular case, and the other 2 are resolution and calibration. So you cannot see, since you cannot see the formula, let me show you what I mean. I could be, in some sense, perfectly calibrated by doing the following. Let's say I'm predicting, someone tells me, I want you to make predictions about all the football games that will be played in the Champions League in Europe next season. So there'll be, I don't know, maybe 150 games going to be played. And I'm going to give you you have to give me the probability for each game of the home team winning. So I can look back and say, over all these years that the competition is taking place, the home team wins 60% of the games. So I'm going to say for every single game, home team wins, probability 60. Home team wins, probability 60. I will be calibrated because my proportion of prediction is going to match the reality. All my judgments are going to be right here, right? They're going to be one huge circle. So on average, I'm going to be right, but I'll have absolutely no resolution. I have absolutely no ability to differentiate between cases where it does and it doesn't happen, okay? Or I can say, oh, what's the probability of a rainy day in New York? 33%, 33%, because it rains 1/3 of the days, and then on average I'll be right. I'll be totally uninformative because I will not be able to give you any information that will help you decide to carry an umbrella or not, right? What it means to have high resolution it means that your points should be spread out, and that you'll be able to distinguish very well between things that happen, events that happen, and not. Here's another way to look at the same thing, which in many ways it's not quite as popular, but I think it's more informative. So in this is a method that Frank Yates from University of Michigan kind of trying very, very hard to push. So the way to read this is as following. These are the same data, by the way, exactly the same data. On the left side is the probability that all the days where it doesn't rain. These are the distributions that people assign to rain when in fact it did not rain. These are the probability distribution of all the forecasting days in which it did rain. So what you see that these are 2 distributions, and what you see that the mean of this distribution. What do you want? What would you expect to see? You would expect ideally to see everyone either in this corner or in this corner. That will be something that will be perfectly calibrated and perfectly discriminating. What you see, and that I'm not going to have time to go through all these lines, you can calculate what's the probability that you assigned for days where it didn't rain, and I think it is, I can't see. And you want to see that the probability of this distribution is higher. You want to see that these 2 distributions are as far apart, as separated from each other, and so on. There are various ways of quantifying how diagnostic your judgments are as a function of how your two distributions are in differentiating between these 2 terms. So what do our empirical data show? When you look at many studies of cases where people may make judgments, and so you can imagine a variety of patterns that will show up. For example, you could find calibration curve like calibration curve A, which will be over prediction. Calibration curve B, these are all hypothetical, right, which would be underestimation. Curve C, which has this shape, this is curve C, that is too extreme, pushes toward the extreme. Curve D, which means that is too regressive. And of course, you could be calibrated, which means that you're on the diagonal. So these are kind of the possible patterns. And what it turns out that we find in most studies, we find this pattern of people of over extremity. In other words, of people over predicting, and something that's interpreted as meaning that people are overconfident. So when they say 100%, when they say it will happen 90%, let's say away from 0 and 100, we'll say it will happen 90%, it actually happens on average only 70% of the time, okay? So this is what we call, this is the typical pattern of overconfidence, which is of over-predicting, having judgments that are too extreme, compared to reality. Another typical empirical finding in this context is one of what we call the hard-easy effect, that the degree of overconfidence is more extreme for events that are hard, okay? So, if you kind of arbitrarily or judiciously, differentiate between events that are hard and easy, the miscalibration is more extreme for hard events. This is where the judgments are more off. And there are a variety of explanations, and I'm not even sure that I have time to go through that, because I'm about 1/3 of my first lecture and I'm about 5 minutes out of time. So, okay, let me very quickly say a few words about. You tell me when to stop. I can go on, but you tell me when to stop.
Yeah, you have 7 minutes.
7 minutes? Okay, all right. So let me say a few words about factors that affect the probability judgment and can account for some of the differences between what you would expect to see and what you actually see. And so this is my own way of dividing them into things which are cognitive in nature, which are reflections of the way we think about the problem and how we approach the problem cognitively. Things that are motivational, that have nothing to do with the cognition, but really about kind of how we are primed to address a problem because of a variety of either conscious or unconscious motivations. And things that really just have to do with the structure, what you would call the institution, the structuring of the problem, how the items are presented, how they are framed, how we pack and unpack them, and so on. So the work that has been by far the most popular is the work on the cognitive. And you wanted to talk about this a little bit?
Yeah, as I mentioned, I really just heard.
Okay, so just to give you a sense, we don't have time to go into that. The idea is the following. I think actually often misrepresented, so it's maybe a good idea to present it the way I think it should be. Is that when we deal with this problem, you ask, what's the probability of some event? What you do, you go through a process of search of your memory, you elicit, you kind of recruit reasons for and against, you think of examples, and so on. And the natural thinking process that we invoke is one that is guided by principles which most often, or for the most part, are perfectly in line with probability theory, but occasionally deviate from probability theory. And so this research program of heuristics and biases has identified a variety of such. So the best well-known is the representativeness one, which is that you judge the probability of an event to the degree to which it is representative, you perceive it as being representative of the model or the process that is generated. And the Linda example is a typical example. We overestimated how likely it is that Linda is going to be a feminist bank teller, because she was so representative of of what we think as the prototype of a feminist. Another example, which I've done a lot of work on my own research, on perception of chance. So imagine that you have to do the following task. You have to simulate the events of a random sequence of events. So for example, imagine tossing a coin again, and write down what you would expect the outcomes to be. So it's a sequence of heads, tails, heads, tails, and so on. And there's a long tradition of doing this kind of stupid, boring work in psychology. I can't remember. I've done many experiments of this type. I remember once, the student didn't know a subject coming out of some of my experiments, talking about how boring and stupid it was, and said, well, that just got me promoted. Anyway, but so the idea is that you ask people to act as if you are a coin, all right? Heads, tails. So to what degree will the kind of sequence that people generate match or mismatch what you would expect from the result of a realization of a Bernoulli process with probability 0.5. So people on average get it right. I mean, on average, they get 50% heads, 50% tails. What people do, they act as if every single short sequence has to be representative, that's what the word representative, of the process. So that means that if even if you look at blocks of 10, they make every block of 10 to be equal 5, 5, which means that they are underestimating the variance of the process, and which means that their sequences have way too many alternations, heads, tails, and way too few short sequences, okay? So let me give you the sense. If you ever look in a book of random numbers, right? A table of digit numbers, it's quite likely that you'll find a page that has only even numbers. And there are pages that all the numbers on the table are even. Because if the table has to be balanced, not that every number and every double, every triple, every quadruple, every quintuple will be equally likely, you must come up with some page situations where half a page is all even. You look at it, it doesn't look representative at all. It doesn't look random at all. Where are all the odd numbers? Well, this is, the complexity of a random sequence. You have to be sometimes locally non-random to be globally random. Well, when people judgments about chance do not accept that because they seem so unrepresentative of a chance event, and therefore, because the thinking is driven by how representative it is, right? Then people's judgments, perception of chance are wrong. That's why so many football coaches are fired after they lose 4 or 5 games. They never allowed a chance to develop a real record. Not only football, but I mean people trend to seek and to see pattern. They expect to see particular patterns, even in very, very short realization of process that really, in order to express all their features, need to be allowed to run in the long run. So that's representativeness. Availability, so maybe that's the last thing that I'll say, and then I'll quit, and then I'll have to rethink what I'm presenting on Friday, is that you judge probabilities to the degree to which you assign probabilities to the event to the degree that instances, examples are easily brought to mind. You can easily simulate them or think about them. So although it's not a probability judgment, here's the experiment that explains it best. I want to ask people to evaluate what is 10 factorial. And I'm not going to use the term factorial, but I'm going to ask to half the people, I'm going to say, please tell me very quickly what's the result of 10 times 9 times 8 times 7, ... I want you please to evaluate what will be the product of 1 times 2 times 3 times 4, ... times 10. I'm asking you to do the same judgments, but I'm basically starting you at one point and starting you at the other point. And since you don't have time to do the calculation, as you clearly imagine, but you're starting at different points, the results are going to be significantly different from one another, and they're going to be larger in one group than the other. So this is a combination of both availability, because I started you with an anchor which is high, and so I made it available to you. But the other thing which is really that may be very important to climate change, is for the following example from a paper by Slovik and Barbara Coombs and others. When they ask people to judge, subjectively, based on their experience and understanding, the frequency of various causes of death in the population. Okay, so they have about 40 or 55, things like heart attack, breast cancer, and accidents, and so on. And of course, these frequencies are known because they are tabulated in vital statistics in every country. And then you can compare, whether people are right, what they overestimate, what they underestimate. And the result, which is that's where the availability comes from, is that people are biased. People are overestimating certain things and clearly underestimating other. What they're totally underestimating everything that has to do with natural causes. I mean, all these people who go at age 17 to the hospital and die for whatever, it comes natural and no one think about it. People are overestimating things from accident. People have to do, on airplane crashes, people being struck by lightning and things of that type. And what you can show is that the degree of over and underestimation is highly correlated to the degree to which these causes of death are reported in the daily newspaper and the daily news. Things that are vivid and that are worthy of, men struck by lightning on golf course and so on. That's the kind of things that are being overestimated because they're very vivid, they come to mind immediately and so on. So it is these kind of things affect the way we make probability judgments, right? And so the reason we do that is because 95% of the time that's fine. But occasionally, in rare cases, they are getting us into trouble and they are moving it in the wrong direction. So I'm going to stop here, okay? All right, so I'm happy to answer any other questions about what the things I meant that I talked so far. Yes?
So I would like to go back to the smoker example you gave. So 8% believe a smoker will die from cancer, 20% believe he will not die. There's 60% of people that think or don't have a clue or basically they say he neither dies of cancer nor he dies not of cancer. So
No.
How do we interpret it?
Okay, so that's I think that goes to a very, very good point. This goes to a very good point. I think it was the first point in my three-way typology, is that the first thing you need to make sure that everyone understands what is exactly the nature of the event that you're judging. So in this case, what you're describing is a situation of someone who doesn't really understand. So because the event was not precisely defined for that. So the way, in this example that I gave with cancer and smoking, to think about is the following. What you tell a person is, imagine we take a random sample of 1,000 people from the population of Italy. For every single person, we record the following two pieces of evidence. One, did you smoke, more than, did this person smoke, and you can have a definition of smoking, right? At least so many years, right? Did this person is a smoker or was a smoker, yes or no? One. Secondly, is this person, by the age of 60, has cancer or not? So you cannot say, you cannot say neither, because imagine there are two pieces of evidence. It's like saying we take for every person we write on a card, smoker, non-smoker, cancer, non-cancer. And what I'm asking you to say, if I'm going to take one of the 1,000 cards at random, what are the chances that I'll get one that says smoker, cancer, smoker, non-cancer, and so on, okay? And by the way, here's an interesting aside. I'm going to take 2 more minutes. This is very interesting of what people think about smoking and cancer, because this is, and this has more to do with perceptions of risk. When tobacco companies were being sued for, causing people to die of cancer and so on, the argument, in most cases, was as following. People were making informed decisions. People know what the risk of dying the probability of dying is, and they were making a utility, basically a cost-benefit analysis, right? And she said, and the decision has nothing to do with us misinforming them or lying or anything, but people simply saw that the long-term utility of smoking over their lifetime far outweighs, the possibilities and the damages that smoking can do. And the proof in many cases they were presenting is the following. Results from many large-scale survey in which people were asked, what do you think is the probability that someone who smoked for so many years, so many cigarettes, is going to die of cancer? And what do you think the probability is? What do you think the probability that someone who is, let's go, a heavy smoker, or whatever is defined, will eventually die of lung cancer? Ballpark. Who thinks it's more than 20%? Who thinks it's more than 10%? Okay, so epidemiological estimates range between 12 and 15%. If you administer surveys to large population and you calculate the average probability, you get somewhere between 19 and 25% from one survey to the other. So the real risk is 12 to 15%. People think it's over 20. It's not that people underestimate the risk. People, if anything, they overestimate it. And actually, if you take the surveys and you break the smokers and non-smokers, the smokers are just as high as the non-smokers. And therefore, the argument was, an expected utility. Why would you blame us for people who assign much higher value from the pleasure from smoking than from the discomfort of dying earlier than others anticipated them? Okay. Okay, so very hard to argue, but anyway. So yes.
So when you're talking about ambiguity,
I didn't talk about ambiguity. I'm sorry. Okay.
When you gave the example of
Right.
highly likely,
Right.
I think of the IPCC
Right.
and the way they frame one of those.
Wait until Friday. I'm going to show you the definitive study. Right.
So I was wondering how you can elicit sophistication of judges. That is, suppose the judge has an idea of what should be the distribution of probability has to assign to events and how this influences his assignment to each single case. So for instance, I don't know if it matches too much, but there are professors that want to assign grades according to normal distribution because they say that IQ is normally distributed. And
so is height, so what?
Exactly.
Okay, never mind.
There is an issue where really judges try to match some,
Okay.
some prior about the total distribution and then the judge...
I know of cases where they do this because the dean sends a memo. We don't want too many, we want to prevent grade inflation, but I think you're right. Okay, yeah, so.
Can you elicitate it and what would be the effect on your...
So what do you mean? I mean, maybe I'm not sure I understand the question.
So I think that, for instance, in climate change, that's one issue because these are experts. So most probably they studied statistics. They know what are the.
So I don't know if you're going to talk about it, but there are I know of at least 2 or 3 or 4 studies. Mostly, I'm thinking of studies by Granger, Morgan, and his group, right at Carnegie Mellon, who have done, and they are published in. I can't remember. I have them on my laptop. And where they went to 20, 25 experts in the field, and they actually listed it. I mean, you say, here are the people that we listed, but they are not identified. And then you have 25 distribution, and you don't know who is who, but I understand that among the people in the field, there's a big guessing game going on. But anyway, and you can see 25 probability distribution, for example, but on climate sensitivity about different experts. So, I mean, I'm answering the same way I've answered earlier. The fact that one is a very good scientist on climate scientist doesn't mean that he or she is also very good at eliciting, at articulating or judging the probabilities. And they may be because of some of these things, but it may be about a variety of others. Some of them purely motivational, and so on. So I'm not sure. I don't know that there is kind of, when we did this review many years ago in management science, so we found weather forecasters are highly calibrated. Other people who do probabilistic forecasts for a living, for example, radiologists, right? So they look at X-rays and they need to say what's the probability that this is malignant or not malignant and so on. They are not so good. So one of the reasons they are not so good is precisely because of the reason that you're alluding to, namely that they almost, as a sense, they cannot help themselves for saying, if I'm going to err, I'm going to err on the side of caution. So if I'm going to, although I think the probability of cancer in this case is only 20%, I probably overestimated because I want to make sure that such cases are. So it's a big issue in some cases with experts who are equally concerned about giving your belief, but also thinking one or two steps ahead and saying, I want to make sure that you interpret my beliefs in the right way and you end up taking the right actions, that they are going to be contaminated by what they see should be the next step. So, okay, so I'll talk again on Friday.